Hi, I've just spent the last few minutes chatting away to myself. I didn't press go live. So sorry about that. Here we go. So we're going to be looking at hypothesis testing for the mean and hypothesis testing for correlation. I've just spent now with the first years doing hypothesis testing for the binomial, so you can watch that one if you need to. You can go back to that one. We're going to be using Nearpod. Yay, we haven't used that for ages. But first, let's talk about the importance of this particular topic in terms of marks, okay? So the big two in statistics, and don't forget statistics is 1/6, right? So we're talking about, I'm in the wrong menu. We're talking about 300 marks divided by, no, 150 marks out of 300 is all of this, okay? All of that. Statistics is 50 marks out of your 300 marks for your A level. Now, out of those 50, the binomial tends to be worth about 15, and the normal tends to be about 15. So you're talking about 30 of 50 just in those two. And then the other 20, this is usually only about like 1 mark or 2. This one's maybe worth 3 marks. And then what's that add up to? 30, 33, 34. Then this one's worth about 10. And this one's worth about 6. Now within that, you've got hypothesis testing here, and hypothesis testing here, and hypothesis testing here. So it's absolutely key to doing well in statistics is getting your head around the hypothesis test. And once it does click, honestly, it's not that difficult. So hopefully it's going to click in the next 45 minutes. So timer on. Except for my phone might die. Can somebody else put a timer on as well? Because I'm on 1%. And then at least you can tell me if the phone does die. Cool. So Nearpod. Go into Nearpod, put in the code, which is this code here. Nearpod is free. And it is AIHUX. Okay. And when you put that in, I'm going to change what you see. There we go. Now, mean of a population. The mu that everybody thinks is true. This is based on past knowledge, or it's what everyone believes. Everyone thinks that's the mean of the thing. And then one guy comes along and he says, no, I don't think that. One person says, I think that it isn't that. It's something else. So all of hypothesis testing, you get these choices. You don't have a choice with H0. H0 is always mu equals or p equals or rho equals 0. So for the normal distribution, it's always mu equals. So read through this information and just write down what is H0 and then what is H1, and then we'll have a look and we'll compare different things. Okay, just H0 and H1. I'll give you 10 seconds. Oh yeah, my phone is dead, so you're in charge of timing. I don't think you're struggling with the H1 at the moment. We've got lots of H0s, but you're not sure what H1 is. So read the question and think about somebody making a claim. Somebody's talking about what they believe is true, And they are saying either they're saying mu is not blah. Everyone thinks it's this, but it's not. I think it is. I think it's changed. Or they're saying it's not that, it's smaller. Or they're saying it's not that, it's bigger. That's literally what you're looking for. I'll give you some more information. Some of the ones that I'm looking at the moment say, actually, do you know what? I'm just going to show you. So don't worry if you haven't done this before. You literally need to read this and look for the mean. What is the mean that everyone thinks? And then what is the mean that one person is claiming is different? Okay. Here we are. That's the mean. The mean is 18. And then we're going to test whether or not there has been a reduction. Whether there's been a reduction. Okay. Hang on. Just not. Why can't I see all your answers? Oh, there we go. Okay, I can see them all now. Okay, so the mean is not 16.5. The mean is this guy here, 18. So it's distributed normally. The mean is 18 and the mean is what goes there, mu. Okay, but I agree with the less than for the reduction, but it should be 18. Mu is 18, mu is less than 18. Perfect, perfect. Yeah, perfect, mu is 18, and then the alternative is less than. So see, a few people have got this 16.5. This one, there's missing a mu, but that's probably not good, not bad, not your fault. Good, so not 16.5, basically. Excellent, and no one's put less than or equal to, which is great. Perfect, right. So we've got our hypothesis set up now. That's our, like, step number one is the hypothesis. Right, now, normally at this stage, we have to do two jobs. Job number one is to read and find out what has actually happened in real life. What is the actual data from an actual sample? And the size of the sample is really, really important. So it's the actual data that we got from an actual sample of size what? That's what we need to find out. Now, once we found that out, then we're going to choose whether or not to look to the right or to look to the left. And that is just going to be based on how weird it is. If the actual data is weirdly small, don't forget 18 is what we're expecting. If we're expecting 18 and we get something a lot lower than 18, then that's weirdly small. So we're going to do less than or equal to. If it's weirdly big, so we're expecting 18. If it's weirdly big, then you do bigger than or equal to. But there is one more job, and it's to do with this line here. Okay, X is the time taken in minutes to complete the puzzle. Okay, in general, in the world, in the population, well, it's Robert, but the time he takes to complete a puzzle across all mornings ever. Whereas what we're looking at here is X bar. We are looking at a specific sample of a specific size. So the thing that we're actually measuring, the thing that we've got data on, the actual data is not from all things ever. The actual data is from a sample of size 15. So what we need is a new distribution, which is X bar, because X bar is the sample with a particular size. So X bar is the mean time to complete the puzzle out of a sample of 15. Now, it's not binomial. We don't put the n inside there, but it's a different distribution from the first one. The first one is normal, 18, 3 squared. The second one, the x bar, is normal. Didn't write in normal. It's normal. And then what you need to learn is that it's normal. Didn't write it again. Normal 18, comma, and then it's the standard deviation or the variance divided by the number, the size of the sample. That is the most important thing. So I'm going to write it. I'm going to put a star here and then link it to over here and remind you that x bar is normal, the same mean, but you divide the variance by the sample size. And that is what we're going to put in our calculator, x bar. Okay, so let's tie all that together. On your Nearpod, I'll give you a fresh Nearpod. No, it's not a normal approximation. It's that, right, so you've got the whole population, right? Imagine it's not days. Imagine it's literally everybody in the whole world. And the mean of everybody in the whole world is 18 and the variance is 9. Now, if I take 15 people out of there, then the variance is going to get bigger relative to each other because I'm not going to have as many people. I'm only picking out 15 of them, right? So if I pick out 15 and find the mean of those 15 and then put them back in, it will be ish 18, but might be lower, might be higher because I didn't do everybody, I only did 15. And then I pick out another 15 and then I find the mean of those and then I put them back. And then I pick out another 15 and I find the mean of those and I put them back. And I pick out another 15 and I find the mean of those and I put them back. And somebody somewhere is jotting down all of the means that I get. The sample size is always 15, but I just pick out random 15, find the mean, put them back. Another 15, find the mean, put them back. The standard deviation of that, if you had only 2, if your sample size was 2, so you pick out 2 people, find the mean, put them back, pick out 2 people, then the variance, the extent to which they're going to vary between each other is not going to be the same as the variance over the whole population. So if your original variance is well, whatever, and then you take a sample of size 1 million, so you take 1 million people and find the mean, it will be about 18. Then you choose a different million and find the mean, it will be about 18, and they'll all be really, really close to 18 because 1 million people is nearly everyone, and I know that if I take everyone, the mean is 18. So the bigger my sample size, the more that each sample's mean is going to be close to 18. And therefore, because that each sample's mean is going to be closer to 18, they're varying less. The variance between the means of the different samples of size 15 will start to vary less and less and less as I make n and bigger and bigger and bigger. So the bigger I make n, the smaller the variance between the different means. Whereas, let's say I pick a really small n, then if I pick out, like n is 5, I take you 5 people and I find the average, and I take you 5 people and I find the average, and I take you 5 people and find the average. Even though the average of all those averages is going to be 18, there'll be way more difference between them, because when I only pick out 5 people out of 1 million billion, I might flukily pick out everybody who's like tiny. So my mean of my samples is going to vary a lot more, which means that the variance of the means is bigger. So we are looking here at a sample of size n from everybody. The bigger the n, the less it's going to change as I go from sample to sample. That's why you're dividing by n, to take that into account. So new thingy bobby. This one should be plain. This is what I want you to write on. It's for this particular question, okay? I want you to write on, I'll do it in black here. I want you to write on probability X bar, and then I want you to choose less than or equal to or bigger than or equal to. And then I want you to look at what the result was that actually happened out of the 15. What is the actual result from the sample size 15? And then you're going to use your calculator to find the answer. So when I show everybody's screens, it's going to have probably X bar is less than or equal to, or X bar is greater than or equal to. Then it's going to have the actual result from sample size 15, and then you're going to get your calculator to tell you what that probability is. Now, when you go into your calculator, you're going to tell it that you're doing normal CD. It's going to ask you what the mean is, and you're going to tell it that the mean is 18. And it's going to ask you what the variance is or what the standard deviation is. So the standard deviation is going to be 3 divided by the square root of the sample size. That's what goes into your calculator. No need for Z. Don't need Z. The only time we need Z, I know why you're doing that, because you've been taught that you need to use Z for hypothesis testing, but you really don't. You really don't. Do you want to try it not using Z? Because it's easier, because then it's more like normal distribution. You don't need Z. The only time in the normal distribution, the only time we use Z instead of X is if we don't know the mean or we don't know the variance. And we do know the mean and we do know the variance. So there's no need. Okay, because what we're trying to find here is something that we can compare to alpha. You don't, it's going to give you the exact same result if you find Z or don't find Z. It's going to give you the exact same result. What you're doing is you've got this line, which is X, which has got a mean of 18. You've got the actual result that actually happened, and you're asking the calculator how big that is. Now, if we didn't know the mean of X or didn't know the variance of X, then the calculator wouldn't be able to tell us this area. So therefore, what we would do is we would change it to Z, which has got a mean of 0 and a variance of 1. And then you would change your 16.5 into Z, which is minus 1.93. And then you'd ask the calculator, what's the area to the left of minus 1.93? But you don't need to do that because the calculator can just tell you the area to the left of 16.5. Okay, I'm ready to show you what you've written. Okay. So I don't think the area to the left can be 15 because the total area is 1. So I agree with that bit that you've just rubbed out. I agree that what we're looking for is less than or equal to 16.5. Definitely that's what we want to look for. What is the area to the left of 16.5? Apparently it is 2.6%. Perfect. I mean, this looks perfect to me. We're doing less than or equal to because 16.5 is weirdly small, and we get 2.6%. Oh, hang on. I didn't get rid of your names. Hide student names. There we go. Unless you're proud, you can be proud. Okay, perfect, perfect. How far to the left is 16.5? It's in the bottom 2.6% of weirdness. Perfect, perfect. Excellent. This one's getting there. We just now need to work out that actual probability. I think this, now it's not 15. It's less than or equal to the actual thing that actually happened. Less than or equal to 16, because 16 is what actually happened. 16.5 was the average. Perfect, perfect. Now, the only thing that I would say about all of these is that none of you have drawn a little picture. And with the binomial distribution, if you get into the habit of drawing a number line, and with the normal distribution, if you get into the habit of drawing a little picture, it just makes all sorts of things a lot easier. Now, the one that you're looking at on the screen at the moment, this is classic, not bad teaching, but classic confusing teaching that's gone a bit too fast, so things have got muddled up, okay? Now, this is the sort of thing you see for a two-tail. And you don't even need it for a two-tail. You don't even need it then. You never need it, really. You never need to see this. What you're doing when you choose, the reason why we only need to do one is because 16.5 is either weirdly big or it's weirdly small. It can't be both. It's not weirdly big and weirdly small at the same time. The mean of the distribution is 18. If the mean of the distribution is 18, then 16.5 is weirdly small. Therefore, we need the probability that it's less than or equal to. X bar is less than or equal to. Nothing to do with both. It can't be weirdly big and weirdly small at the same time. Okay, so we have now got, let's see if there's anything else interesting. No, lots of 15s here. Why have we got lots of 15s? There's like 1, 2, I think there's like 3 15s out of maybe 10, which is interesting, right? Why would we have 15 less than or equal to 15? I'll go back to the question. It's people who put 15. Oh, continuity correction. We don't need a continuity correction here because we're not moving from binomial to normal. Okay, so the situation where we would do that is where we've got a binomial distribution and we want the probability that X is less than something, or the probability that X is less than or equal to something, or the probability that X is bigger than something, or the probability that X is greater than or equal to something. And then we want to change that into a normal distribution. So what we do is we change the distribution to normal, and it'll be NP, NP1 minus P. And then we also change the actual probability, but not AQA. This is for EdXL and OCR only. What you do is you then change it using the continuity correction. But if you draw the line that I said to draw for the binomial, it's easy peasy. So let's say that this is 4. So if we have 1, 2, 3, 4, 5, less than 4, less than or equal to 4, bigger than 4, bigger than or equal to 4. The continuity correction is this number here that it's pointing at. That's the continuity correction. So in the first case, we would change it to, let me just move this out of the way. So we've gone over to being normal, NP, NP1 minus P. This would be the probability that X is less than or equal to 3.5. This one would be the probability that X is less than or equal to 4.5. This would be the probability that X is less than or equal to greater than or equal to 4.5. And this would be the probability that X is greater than or equal to 3.5. So you can come up, I've known students come up with the most creative ways of remembering. If it's less than, then it's less than, and it does this and it does that, and it just draw that number line, and then it's obvious. Wherever the line is, that's what the continuity correction is saying. But the continuity correction is for when you have a problem which is binomial and you want to go and use your normal distribution. Here, we've just got a normal distribution. Everything is normal. Normal, normal. We want to find the area to the left of 16.5 because that's the result that actually happened. Actual data from actual sample size 15. This comes out to be 0.02 something, 0.264. And can you see, whoever was at the top, top left, can you see that you don't need Z? I did not use Z in my calculator. I can just go straight into my calculator, say I want normal CD, the mean is 18, the standard deviation is 3 over root 15, and then ask for the area to the left of 16.5, and it tells me. Okay. Now we do our comparisons. So what are we going to compare it with? Well, if it was 2 tails, if the person is saying, I don't know, I don't think it's 18. I don't think it takes him 18 minutes to do a jigsaw puzzle. And that's all I'm saying. Then that is a 2 tail. That means I've gone in either direction. I'm basically saying, I don't think it's 18, but I'm not facing in one direction or the other direction. Whereas if I say, I think it's bigger or I think it's smaller, then that's the 1 tail. If it's 1 tail, then you compare with your significance level. And if it's 2 tail, you can remember because there's a 2 there, you divide it by 2 if it's 2 tail. Now this one says, test whether there has been a reduction. So the person is saying, thanks Katie, the person is saying it's got smaller. They're claiming that it's smaller. We're looking for it to get smaller. That's 1 tail, so we just use the 5%. So in this particular case, we would say 0.0264 is smaller than 0.05. And that is small, 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 means very, very, very weird. And that means that we're going to reject H0. Is that? I'll be 1 second, there's someone at the door. I think it's for next door. I think it's for next door. Right, let's have a look at the next one. Okay. I would like you to, as quickly as possible, submit H0 and H1. That's all we're doing. So Ibrahim, you were asking about whether or not you include the less than or equal to in the for a continuous distribution. It makes no difference. So the probability that it's less than or equal to is the same as the probability that it's less than. It makes no difference. Oh, the code is AIHUX. Yeah, it's a website and an app. You can just do it on the website as well. Okay, so what are we going to have for our H0 and our H1? Let's have a look what you've got. Okay, right, we've got, that was all the first years that are gone now. Oh, everybody is agreeing. Everybody is agreeing with mu is 11, so the mean is 11. Everybody thinks the mean is 11, but somebody is claiming that it isn't 11, okay? So you can see that pretty much everybody's in agreement there. So let's have a look at the actual question and see if we can see the evidence for you being right. So the normal mean, the doctor's surgery has a mean of 11. I agree, the mean is 11. Test whether or not the doctor's belief is correct. What's the belief? The doctor believes that it's changed. Perfect. I agree with you. It's changed, not equal to 11. Now, neither of those, that decision, whether to go bigger than or less than, for the next bit, that's irrelevant. What I'd like you to write down now on the next screen is, I'd like you to write down that X bar, you don't need to write this bit down, I'll write it down for you. X bar is distributed normally. The mean is going to be the same as the original mean. And the variance is going to be the other variance divided by the sample size. Now, actually, in this case, they're not telling us the variance of the population, but we can work out the variance of the sample, and we can use that to model the variance of the population. Okay, so normal X is distributed normally, the mean is 11, and the variance is, I will do this for you, 18737.712 divided by 120 minus the mean squared, which is 1411.2 divided by 120, close bracket, squared equals, so it is 17.85. So that is the population, and this is the means of the samples of size 120. And you are doing the probability of X bar. So what I want to know is, what I want you to think through is, what am I doing? Am I doing X bar less than or equal to? And what number? What goes there? And what is the answer? Or am I doing the probability that it is greater than or equal to? What goes there? And what is the answer? Okay, I'll give you a new slide. Oh no, I didn't mean to do that. I wanted just a blank one. How did I get 17.85? I did the variance formula. I did the sum of t squared over n minus the sum of t over n squared is the variance. Okay, so you're here at the moment. This is what you should be writing. It's either going to look like that or it's going to look like that. You're having to make a choice about whether it's bigger than or equal to or less than or equal to. And that choice is based on the actual data from the actual sample. And then you need to feed the information into your calculator in such a way that it gives you the right answer. Haven't got any answers up yet. I'll give you another 30 seconds. Most people have chosen what they're going to find, like this number here. This number here is the actual data. So what really happened when he did the 120 and measured the mean time taken, what was the actual mean for that 120? That's what goes there. Now, what mean were we expecting? We were expecting 11. So the mean from the actual data, is it weirdly big or weirdly small? Basically, compared with 11, is it weirdly big compared with 11? In which case, that's what you should write down. Or is it weirdly small compared with 11? In which case, that's what you should write down. This one, for if the actual result is weirdly small compared with what we expect, which is 11. And this one for if the result is weirdly big compared with what we expect, which is 11. No need for any continuity correction because it's all normal. So we're just doing normal, normal, normal. And because the standard deviation, the variance goes to the variance divided by n. So the standard deviation goes to the old standard deviation divided by the square root of n. And what you write, when you write this down, that's the mean and that's the variance, not the standard deviation. So it's when you, this is what you put in the calculator, right? You put in standard deviation, not variance, but what goes there is the variance. X is not 120. No, this is not the result. They didn't find out. It would be a bit weird if they did, didn't they? If they found out that the mean time for out of this 120, the actual data says that the mean of the 120 people, the average time they waited was 120 minutes, and we're expecting 11. How do you get the actual mean? You know how you get, this is the data, this is the actual data. Yeah, that one divided by that one. Exactly. It's the actual data. In binomial, they sometimes like tell you like, we did it 15 times and we got 7. So the actual data is 7. In this case, the actual mean from the actual mean from actual data. That's what goes there. And then once you've got that actual mean, you have a choice. Are you going to go less than because it's weirdly small, or are you going to go bigger than because it's weirdly big? Okay. Right. Do you want to see what everyone's written so far? So I'm checking 3 things here. I'm checking that you know what the actual result is. I'm checking that you know whether to go less than or bigger than. And then I'm checking that you can use your calculators to find that number. Okay. Let's have a look at the carnage. Here we go. It's looking good. It's looking good, people. Well done. You're getting it. It's easy, right? It's easy when you get it. So 11.76, I totally agree, because it was the sum of all the t's, 1411.2 divided by 120. That was the actual mean of the actual sample that they actually did. Now we're expecting 11, and we actually got 11.76, which is weirdly big. Or is it, wait, is it 17.6 or 11.76? Yeah, 11.76 is weirdly big. I mean, I know it's not huge, but if we're expecting 11, then 11.76 is weirdly big. So we want to go to the right, okay? So this is correct. Greater than or equal to, greater than or equal to. Not correct. Whoever this one is, it should be greater than or equal to 11.76. So the 11.76 comes from it is the data. It's what it all adds up to divided by 120 to get the mean of the actual sample. And then because that's bigger than 11, it's come out weirdly big, which means that we're looking to the right. Okay. So I'm just looking at bigger than or equal to 11 points. Nope. Not less than or equal to, bigger than or equal to. Good, good, good. Okay, 11.76, try not to prematurely round here. So the 11.7 is unnecessarily rounded. There's no need for that rounding. Okay, now let's have a look at the probabilities that we've got. This one is still the wrong way round. Excellent, that one's gone the right way round. Next, we've got any probabilities coming out here. You're just going to stick it in your calculator. Excellent picture. Look how small that bit of area is. The smaller that is, the weirder 11.76 is. The weirder 11.76 is, the more we reject H0. Okay. Have we got any actual probabilities coming out yet? That one is still the wrong side, and it should be 11.76. 0.0244. Brilliant picture. Brilliant. The area to the right being 0.0244. Let's see if anybody agrees. This is still going the wrong way. This is still going to the left. And we know 11.76 is bigger than we expected. So it would be going to the right. 0.024. Perfect. Not quite perfect. See this red one? Whoever wrote this red one, this is important because when you type it in your calculator, you must remember to change the variance. And because you've written an X here, this X, just change it to an X bar. Whoever's got the red one, let's see if we can see it in real time. See that X bar appearing. Just to remind you that it isn't X that we're putting in the calculator, it's X bar that we're putting into the calculator. Okay, lovely. This one, I'm not sure what's gone wrong because bigger than 11.76 is correct, but this is not the probability. I think maybe you didn't change the variance in your calculator. I think maybe you typed in for the calculator, the mean is 8, the mean is 11, and the variance is 17.85. And actually the variance needs to be 17.85 divided by 120. The variance. Okay. So, good, Annabelle. Nice. Right. So the next thing that we would do after this, so we'd find this mean, which we did was 11.76. That's weirdly big. So we're not doing this. We're doing this. We get 0.02. Now we've done that and we've done that and we're down to the comparison. Now, this is the stage where we need to know whether or not the null hypothesis was one of these, in which case we compare with alpha. This guy here compares with alpha, or this guy. And because it's this one, we're going to halve the alpha. So even though we've got 10% significance, we're actually going to compare this to 5%. Okay. How do you get more than? You do 1 minus the answer. So you'd get your calculator and you'd tell your calculator that you want to do normal CD. And you tell it that the mean is 11 and that the standard deviation is 17.85, all divided by 120 square rooted. And then you tell it that x, x is 11.76, then that will tell you this area. And then you do 1 minus to get the little area to the right. So now we're going to compare it with alpha over 2. And this is the point where we look back up and see how many tails there were, or whether or not it was both ends or only one end. And we would say 0.02 is less than 0.05. Now, does that mean we reject or don't reject? Stick it in the chat. Reject H0 or do not reject H0. Courtney, yeah, minus 1,000, whatever you want, really. Yeah. Reject H0. We reject if it's teeny, 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 teeny. Teeny tiny, reject. Perfect. We're going to reject. So we reject H0. And then we write there is, where's the test? Whether or not the doctor's belief is correct. There is evidence that the average time for a consultation has changed with the new regulations. Yes. Right. Do reject. Sarah, do reject. Because tiny probability means, what this means, this number that comes out here, the thing that you find at this stage, what that means is how weird. Think of it as how weird. This is how weird is it? Outside my house on my doorstep right there is one person who's very, very drunk by the looks of it, and the other person who's trying to persuade them to stand up. I'm just gonna check if she's okay. Is she okay? Is he being nice to her? This is what happens if you live right in the center of town. Sometimes we go out because people are not being nice to people and we go and just try and help out. But I think he's being nice. Oh, right. VJ is saying, try not to think about testing H1. We're never really testing H1. No, we are testing whether or not we have enough evidence to reject H0. That's what we're always doing. Always think of it that way round. You start under the assumption that H0 is correct. You do a test, and if it comes out really weird, like unlikely, so unlikely that it makes us go, all right, maybe it's not that then. But it's always about the H0. Yeah, the H0 is either going to not be rejected or rejected. That's what's going to happen at the very end. We either do or do not reject H0. And the reason for rejecting H0 is that the actual data that we actually got is so unlikely to have happened if H0 is true. So we reject H0. Yeah, so for the variance in the calculator, it would be the square root of 17.85 over 120. Yeah, the square root. Explain whether in answering part A it was necessary to assume the consultation times were normally distributed. What did we do in part A? We tested that normally distributed as opposed to what? As opposed to distributed how? Yeah, I don't know what that one's going on about, part B. I'd have to look at the answers. This is in the course. The wordy ones are just so hard to pin down exactly what they're asking for. Right, let's have a look, because we've got 5 minutes max, and I want to have a quick look at the correlation ones, okay? So H0, always no linear correlation, always. Always, always, always. H0 is always, there is no linear correlation, none, okay? Then what you're going to do is you're going to use the tables to find the critical value of R. And you find the tables by looking down the alpha and across the N. And the N is the sample size, actual sample. And the alpha is the significance of the test. And obviously, same as before, it's half that if it's a not equal to. Okay, so for this one would go to half of alpha. Otherwise, it would just be alpha. And then you look that up in the table. So you should have these tables in your book, and you work out the actual critical thing. Good, thank you. So the critical thing you find yourself by looking down the alpha. So in this case, we've got 5% significance. But what is our H0 and H1 going to be? Let's have a look. Do you want to do this on a Nearpod to compare your answers? Let's do it super fast, okay? There. Okay. Super fast. H0 is rho equals 0, always. H0 is rho equals 0. H1, what is the claim? What are they claiming? What do they think? What are we testing for? Do we think that there is correlation? That's either way, just it's not naught. Do we think there's positive correlation? Is someone saying, I think there's positive correlation? In which case, the H1 is that rho is bigger than naught. Or do we think that there's negative correlation and we're testing for negative correlation? Or somebody's saying that they're correlated negatively. So as one increases, one decreases. That tells you what to do with your H1. Okay, chuck that down quickly. Perfect. H0, rho is 0. H1, rho is bigger than 0 because we're testing for positive correlation. We're actually claiming that as one increases, the other one increases. Perfect. Okay. Have you got tables? Are you able to look in your tables? We've got a one-tail test because H0 is just going to the right, just bigger than. So we need to look down at 5% for the alpha, and the sample size is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 babies. This is the sample. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So there are tables that look like, well, you'll have them in the back of your textbook. I'll grab a textbook. Not in that one. They're in your textbook. I haven't got a textbook next to me. Have I printed one out? Can someone tell me what they are? What that number is? So you look down there because it's got alphas across the top and then it's got n's down the side. So we are comparing an alpha of 0.05 and a sample size of 9. And what we want is that number in there. Oh, great. You've all found it. Brilliant. Okay. So the number is 0.5822. Okay. Time has gone. Let's just quickly finish this one then, and then you can have a go at it. So process is exactly the same. Always the same row. Row is 0. Always, under all circumstances. Then you choose one of these. You go to the table and you find that number. That's your critical R, which in our case is this. Then you're going to compare that to the PMCC from the data. Now, this data gives you a PMCC of 0.972. So we're going to compare those two. And now we have to decide whether or not, this one's the easiest. Normal distribution is the hardest. This one's the easiest. We've got to decide whether or not to reject H0. Now, it's the same idea as with the normal and the binomial. If we are down this end or down this end, we're going to reject H0. So what happened before was that we found that area and then found out how small that area was. In this case, what we do is we imagine a number line. And then here is your critical R. And there is minus your critical R. They don't bother putting it in twice in the book because you can stick a minus on. And if we're here or here, it's the same thing. If we're in an extreme end, then we're going to reject H0. So this is where we're going to reject H0 down here. And this is where we're going to reject H0. So because this number 0.972 is bigger than 0.5822, that means we're down this end. If we're down this end, then we're going to reject H0. So we reject H0 and we say there is evidence of a positive correlation. Okay. I'm going to break all of the rules and show you this one, but I'll just talk you through it and then I'll let you go so you can have a break before Chem. Okay, so H0 is always, row is 0. H1, who is saying what? Who is saying what? The data shows the height. The PMCC comes out to be that. Test for negative correlation at the 5. Test for negative correlation. Negative correlation. We go to the tables and we look up 0.05. I didn't halve it because we're not doing two-tail. It's not that somebody's saying there is, it's just that they're saying, go look to the left, actually look for negative. So that's why I didn't halve it. The sample size is 1, 2, 3, 4, 5, 6, 7, 8, 9. This number here will be the same as what we got before because it happens to be 0.05 and 9. So that number there, the critical R, was 0.5822. So the other end is minus 0.5822. That's that number there. Anything in here or in here as the PMCC for the data, we're going to reject H0. So in this case, we would say minus 0.975 is less than minus 0.5822. So it's extreme, it's on the outsides, it's like having a tiny, tiny bit of area. So we would reject H0. So there is evidence for linear correlation. Phew! I hope that helped. I hope I didn't just confuse you with all of that. I would recommend that for the next 24 hours, I'll go and I think I already did this, but if not, I'll go and make sure they're all turned on. I would suggest that you do some practice, make some notes. I think there's 2 videos on hypothesis testing for binomial, and there's one for normal and one for correlation. So literally you could complete all those 4 in about half an hour, definitely within an hour. And then you know you've got all those notes complete. Don't forget our target for the next week, this week, is to finish your A-level notes. Just finish them. Just get them done. And then we can start on the real fun, which is the TT method. Okay. Lovely to see you all. I know I broke the rules. But yeah, 45 minutes isn't enough, but it never is enough. That's the point, really. The squiggles that I was drawing is just highlighting to you that the end, what counts as the end is all the bits past the critical R that you get off the table. And if you're in one of those critical ends, then you reject H0. Exactly the same as if you're in a normal. If you're down that end or down that end, which is shown by a tiny, tiny probability, then you reject H0. Exactly the same with the binomial. If you're down that end or down that end, which is shown with a tiny, tiny probability, then you reject H0. Give it some practice, because honestly, it does click. It does click after a while what you're thinking about and that kind of thing. I will see you tomorrow. Tomorrow we are doing projectiles. So I'm considering the A2 stats done now. The only bit I haven't done with you really is probability, conditional probability. But yes, I will see you tomorrow.